All right, looking at the last lab we're going to do for Chem 111, which is the enthalpy of hydration of sodium acetate. What we're going to do is try to figure out how much heat our enthalpy will be either absorbed or released when we do the following reaction. We're going to take sodium acetate as a solid, add 3 waters to it, and make solid sodium acetate trihydrate. With the note, even though there are waters here, this is called a hydrated crystal, and this is still actually a solid. First of all, this reaction is actually really not doable. We can't add the exact right amount of water to get a solid when we're done here. So we're going to do this entire reaction kind of sideways using Hess's law. Now, Hess's law is going to make a lot more sense when we get further into the chapter, but for right now, we're going to talk about the experiment itself. What you're going to do is you're going to take a sample of some anhydrous. This is the stuff without the water. You're going to record the mass. And once you've recorded the mass, you're going to take and you're going to put the solid that you weighed out. It's going to be between 1.2 and 1.25 grams, and you're going to put it in a test tube. And then you're going to take and you're going to get yourself 10 mils of water. When your 10 mils of water is in a graduated cylinder, when you first measure this out, you are going to get its temperature, and we're going to call that temperature initial. And we're going to pour this 10 mils of water into this container. Now, when we do this, we've got one of two options. The temperature is going to go up or the temperature is going to go down. If the temperature goes up, it means that as your sodium acetate dissolved, and that's all we're doing, is taking our sodium acetate, putting it in water, and making sodium and acetate. If the temperature goes up, and note, we're going to put our thermometer right in here. We're going to use our thermometer to stir this up. And what is actually going to increase in temperature is the combination of the 10 mils of water and the whatever it is. So I'm just going to assume 1.20 grams of the sodium acetate. And it's that combination, that mixture, whose temperature changes. And so what is this? This is going to be called our solution. That is the mixture of the solvent, our water, and the solute, the sodium acetate. So that is my solution. If the temperature of the solution goes up, SOLN for short, then the reaction is exothermic. Because here, if this releases heat and heat comes out, that heat has to go somewhere, and that heat is going to go into that 10 mils of water and the ions of sodium acetate. And so this would be an exothermic reaction, and the temperature of this would go up. If the temperature went down, it would be an endothermic reaction, and heat would be released. And we're going to do the same thing here. Now, for our calculations, we're going to look at the heat gained or lost by the solution, which again is the 10 mils of water. With a note, the density of water is 1 gram per mil, so 10 mils is going to be the same as 10 grams. It's going to be the solution, so we have to add our compound to that. So if I'm doing the 1.2 grams of my sodium acetate, I'm going to have 11.2 grams of my solution. And that is what is going to gain or lose heat. So with a note, the first law of thermodynamics tells us that any heat that is lost by something has to be gained by something else. So we're going to say where heat, and we're going to define heat as Q, that Q that is lost plus Q that is gained is equal to 0. If our solution gains heat, then our reaction, which is our bonds breaking apart here, is going to lose heat. So what are we going to do with this? Well, we're going to go over here and we're going to do our math. When we do our math, we're going to have our mass of our water, which is going to be 10 mils or our 10 grams. You're going to record the amount of this you have. So let's say I've got 1.20 grams. My mass of my solution is the sum of that. My room temperature is wherever I start. So let's say, for the sake of argument, that I'm going to start out at a temperature of 21.5 degrees Celsius. And let's say when I stirred this, my temperature went up to 24.0 degrees Celsius, making my change in temperature with the note delta T is always T final minus T initial. It's how we choose to define it to keep track of the signs of our temperature change. So 24 minus 21.5 is going to equal 2.5 degrees Celsius, and that's going to be our delta T. And our Q solution, our equation for Q solution is our Q is going to equal the mass of the solution, which is this value right here, multiplied by the specific heat capacity, which is going to be given, multiplied by our change in temperature, and we're going to plug that in. We're going to cross out our units. This is going to be my 11.2. That's going to vary, as will your delta T, and you will get a value for your heat for this reaction, or for your heat that is absorbed by your solution. Here I get Q of my solution is equal to 117. My units are joules because my grams cancel and my degrees Celsius cancels. The Q of solution will be 117, making Q of the reaction minus 117 units of joules. Here, our joules are going to be how much heat, in this case, has been absorbed by the solution. And if it's been absorbed by the solution, it has to have been lost by the reaction. You're going to do the same thing for the second one, where you're going to have a new sample of water. It's still going to be 10 grams. You're going to have some of this, it's going to weigh more, and you're going to get a different direction of your temperature. Now, what are we going to do here? We're going to go over here, and we are going to calculate a delta H with a note that our heat Q divided by our moles that has reacted is going to equal a delta H. That is how we're going to define our delta H, where our delta H is our enthalpy. Again, that will make more sense when you do the lecture on this. So if my Q is minus 117 joules, I need the moles of this stuff. Well, I had 1.20 grams. So to get moles, I'm going to need the molar mass. My molar mass of my sodium acetate is 82 grams per mole. So if I take my grams, 1 mole for every 82 grams here, I'm going to get my 1.2 divided by my 82, and I'm going to get a value here of my moles of what is reacted as 0.0146 mole. My delta H is going to be my heat from part 1 for the reaction. That's that negative value for this one. It is going to be this one right here, Q of the reaction, divided by the moles. With a note, we put or tabulate these in units of kilojoules. There's 1 kilojoule for every 1,000 joules. And so I'm going to put that together, and I'm going to get the amount of heat that was released in this reaction in units of kilojoules per mole, and that's going to be minus 8.01 units of kilojoules per mole. All right, now you're going to do the same thing for part 2 and get your delta H of a reaction, with a note that when we calculate the molar mass of this, we're going to take the 82 from the first part, because that's sodium acetate, and we're going to add 3 waters, which is 3 multiplied by 18 grams per mole for my 3 waters. When we do that, we are going to put this together in Hess's law. Hess's law tells us that the enthalpy for the overall reaction is the sum of the enthalpies for the sequence reactions. So your job is going to be to try to figure out how to put reaction 1 and reaction 2 together in order to get this reaction here. And we will discuss that when we get to class and we do Hess's law. And the rest of it, again, will make perfect sense as we get closer towards the end of the semester.